So I'm a fan of the sports writer and video essayist John Boyes, who recently released a 4-part video essay called Full Time, a story about the invention of the telegraph and the development of the first transatlantic telegraph line. He does so by introducing many of the key characters in that venture, including one William Thomson, who derived the law of squares, which they used to compute how long it would take signals to travel across the Atlantic. In his video, John shows the paper that Thomson wrote by panning the camera across several pages and saying the conclusion out loud, but he doesn't go deep on how it works. It is my hope in this video to rectify this, using a more modern derivation. The direction of our derivation will be built on the telegrapher's equations, the idea of which is to treat each segment of wire as a basic circuit, applying the laws one would learn in a first physics course to each, then turning into a partial differential equation by considering all of these segments of wire at once. The model includes the resistance, inductance, conductance, and capacitance of the wire, but Thomson only considered a couple of these factors, and was right to do so. The telegrapher's equations were derived by Oliver Heaviside, who I think is a role model in how I approach mathematics. He was the one who first wrote Maxwell's equations in the vector calculus form that most people know today, and developed operational calculus to solve differential equations in a similar manner as the Laplace transform does today. So the telegrapher's equations begin with this circuit model for a segment of length dx. We have a resistor and inductance in series, and a capacitance and conductance in parallel. The terms in series mediate a voltage drop, and the parallel terms mediate a drop in the current, which we will track in the coming slides. First, we consider the voltage drop using Kirchhoff's voltage law, which basically says that the sum of voltages on a closed loop must be zero. What this means for us in this case is that the difference in voltage across the segment must be the sum of the individual voltage drops, which come from the resistor, governed by Ohm's law, V equals IR, and the inductor, governed by Faraday's law, L didt. Then, dividing by dx and letting that dx go to zero, we arrive at an equation for the voltage gradient. Next, we consider the current leakage, using Kirchhoff's current law, which says that the current going into a point must equal the current leaving that point. Here, that means that the difference between the current entering and leaving the segment must track any current that is lost, and the losses for this circuit is the conductance from that parallel resistor, again governed by Ohm's law, now I equals GV, and the charging of the capacitor, C dV dt. Again dividing by the length dx and taking a limit, we get the gradient equation for the current. Taking these together, we get a pair of equations that describe how the current and voltage vary in time and space, and how they are coupled together. Notice how each parameter from the circuit affects one and only one term. If thinking about current and voltage at the same time is too much, one can also apply a spatial derivative to the voltage equation to substitute the second equation into the first, re-expressing the current in terms of voltage to produce one equation seen here. Solving for the current instead produces an identical equation, other than the dependent variable. One big difference is that every term now depends on some combination of parameters, which in turn affect multiple terms. This combination of parameters is what we'll use to arrive at the law of squares, in this case assuming that the inductance and conductance are both zero. No conductance assumes no leakage across the wire, and no inductance assumes that no energy is stored in the magnetic field, which is used as an inertia for a current. In a low-frequency environment that Thomson worked in, these are both fine assumptions. Doing so reduces the telegrapher's equation to this diffusion equation, and this is what gives us the square law. To get this squaring, we need to impose some initial or boundary conditions. For my purpose, I'm going to say that at time zero, there is no voltage anywhere. But at that time zero, we turn on a voltage source at the location x equals 0. The solution to this equation uses the complement error function, but this isn't the important part for us. Notice that our solution has one function with the argument x times square root rc over t. This tells us that along the spacetime curve, t equals alpha rc x squared, for any value alpha, the voltage will have the same value. This picture highlights how the different values in the voltage response travel, and the farther away one is from this origin point, the more spread out the change of voltage is in time. For telegraphers, this means that the farther you are from the origin, the longer the beeps you hear become. So instead of beep beep, it might be beep beep. And so for any curve t proportional to rcx squared, we are going to be tracking the same characteristic curve. Also, If you want a really janky justification for the law of squares, just take the diffusion equation and cancel out the d's and the v's, and rearrange. This is only rigorous in that it tells us that the scaling law is correct. Now, Thomson's law of squares does present some problems for telegraphy, and obviously it succeeded despite this problem of time stretching. But how was this problem overcome? Well, this is where the work of guys like Heaviside come in. If we assume now that r and g are both 0, we get this wave equation here. Using a similar scaling law justification by canceling d's and v's, we get a new scaling law relating t squared and x squared, which relates x and t directly, so everything moves at a constant speed, 1 over the square root of LC. Now this is idealized, but if you can find good values for L, R, C, and G, you can get the telegraph equations to respond how you want given the circumstances. And this is what engineers will do. Obviously my justification of canceling d's and v's doesn't work in a formal sense, but hopefully based on the previous derivation that I presented, a similar logic will hold. Now if we look at these scaling laws, they produce equations that look like parabolic and hyperbolic curves when drawn on an xt plane. And it is precisely from this picture that researchers classify partial differential equations into elliptic, parabolic, and hyperbolic equations, and why each class behaves so differently from one another. I include this last bit as a teaser of what I have planned for this channel in the coming months in math education, so subscribe so that you'll know what my plans are. If you like this video, then like this video. Thank you for watching.